Okay, everyone. Good morning. My name is Rebecca Dzonbeck, and I am happy to kick off our first press conference this morning, first press event of EGU's Fall Meeting 2021. We're going to start with a press conference on the threat from Thwaites, the retreat of Antarctica's riskiest glacier. We will begin with the panelists each giving brief presentations describing their work, and then we will open it up to questions from reporters. And we will end on the hour or when there are no more questions, whichever comes first. Reporters, you will not be able to turn on your video or microphone. This is a Zoom webinar. So if you would like to ask any questions, please type your full name and affiliation into the Q&A box, not the chat box, but the Q&A box. And during the Q&A, my colleague Liza will request that you unmute yourself to ask your question, and we'll answer them or unmute you in the order that your question requests were received. If you'd rather just ask your question via text, you can do that as well. Just type your question into the Q&A box, again with your full name and affiliation, and we will ask it to the panelists on your behalf. Please do use the Q&A function, not the chat box, and you can write in your question at any time, but we won't ask it until the panelists have finished their presentations, and panelists will not be able to directly respond to you in the Q&A box. Please do also make sure that your Zoom name is accurate so that we can find you quickly in the participant list when we go to unmute you to ask your question. You can also raise your hand. That can help us find you quicker as well. Although just raising your hand won't be enough to ask a question. You have to provide your name and affiliation. The slides and the additional materials from this press conference will be posted in the Press Information Exchange on AGU Connect. And we'll drop a link to that in the chat. This press event is being recorded, and the recording will be posted to AGU's YouTube channel and linked to in the Press Information Exchange. Please do bear with us if any issues arise. If Zoom webinar goes down for any reason, we will switch to continuing the press conference through a teleconference line. If this does happen, we will immediately send out an email to all the panelists and attendees with information and instructions on how to access that line. If you have any technical issues during this briefing, please do email news@agu.org. And with that, I will turn it over to our panelists.
Can you go ahead and advance the slide? Thanks. One more time. This is a picture of Thwaites Glacier, one of the largest, widest glaciers in Antarctica. It's huge. It stretches completely across the horizon, even from an airplane. Thanks for looking out the window. This glacier is so large, it covers the horizon from side to side. It's extremely thick. And beneath that ocean water that the ship is floating on, about 6 times as deep as that ship is long, there's warm ocean water reaching the underside of the ice and melting it. And that's why we're here. There's a huge impact from this warmer ocean water eating away at the underside of the ice shelf, and a lot of effects on that interface. That's what we're going to talk about today, is recent research results from the interface between the ice and the ocean along Thwaites Glacier, one of the largest glaciers in Antarctica. Next slide, please. You can see that in this map of elevation change over Antarctica, that there's a large red patch in the left side of Antarctica. And click again, Thwaites Glacier is right in the center of that area of elevation loss. It's already begun to put more ice into the ocean than falls as snow on top of the ice sheet. And so next slide, please. And again, what we're going to focus on is this area of interface between the ice and the ocean. Now in the upper right here is the ice sheet. That series of lines shows how the front of the ice has, the place where it goes afloat, has retreated over the last 20 years or so. And then the gray area is the floating ice out in front, which is evolving rapidly. Click again, please. And here are some of the facts that have caused us to look at this glacier in particular. Thwaites Glacier was identified by both US and UK scientists as being the most important place to study for near-term sea level rise. Within this century, this glacier could all by itself begin to significantly affect sea level rise. For that reason, next slide, please. The US and the UK funded a massive effort, 8 projects and over 100 scientists to study all aspects of Thwaites Glacier. This cross-section shows you some of the geography of the area in a stylized form and all of the different aspects of the ice, earth, ocean system that we're going to study and report on today. Next slide. This international collaboration, as I said, is composed of 8 projects. And each of those are designed to fit together and work together to create a more collaborative and insightful result at the end of the program. We're about at the midpoint of the International Thwaites Glacier collaboration. We've got a few more years to go to assemble further results and integrate them so that we get a better understanding of this glacier going forward. And I think with that, the next slide will be Erin's slide to talk about the changes in the ice shelf.
Thanks, Ted. And it's great that you were able to call in from McMurdo Station on your way out to the ice shelf to collect some of our data that's going on right now. Hi, my name is Erin Pettit, and I'm a glaciologist and associate professor at Oregon State University. And I'm going to talk about the floating portion of this ice shelf that spans that area from the grounding zone where it goes afloat out to that underwater mountain or seamount that's shown in this figure. So the Thwaites Glacier, as Ted said, flows into the ocean across a stretch of coastline that is nearly 120 kilometers in length. Over 1/3 of that coastline, the glacier flows more slowly because it's being stabilized by this floating ice shelf that's attached to this submarine seamount. It's about 50 kilometers offshore. As it's structured right now, this ice shelf acts like a dam, but it's not going to for very long. My team, led by Ted, is heading down and studying this demise of the ice shelf. We also have oceanographers heading down today or this week through Chile on their way to do some work by ship as well. So essentially, there are 3 parallel drivers for the collapse of this ice shelf. And the collapse of this ice shelf will result in a direct increase in sea level rise pretty rapidly. The first is direct melting by the ocean underneath. The second is the loss of grip on this submarine seamount. And finally, the third is the shattering of the ice itself, with numerous fractures propagating at ever faster rates. Next slide. Our oceanography team that's on its way through Chile is going to do an intensive study of water around and underneath this ice shelf. From their last visit a couple of years ago, we already know that warm waters are flowing in off the continental shelf, shown in the pink and red arrows. They're mixing together and causing melting in some key areas, particularly that area circled in black and right behind that submarine seamount. Importantly, what this means is that the ice is losing its grip on that seamount. Next slide, please. We have also found through satellite imagery that the ice tongue on the more western side of this area is now just a loose cluster of icebergs and really no longer influences this eastern, more stable part of the ice shelf. That connection between them, shown by the black line, is nearly gone. Next slide. This split between the ice tongue and the eastern ice shelf has caused the eastern ice shelf to change its flow direction dramatically over the last 10 years. This is the area shown in black, where you can see the white flow lines are moving over towards the left and expanding out towards where the ice tongue used to be. This change in flow direction is also indicative of the loss of grip on that submarine mountain. Next slide. If we zoom in on this seamount here, we can actually see the reduction in contact area over just the last few years. The green was the contact area circled in 2014, and the 2020 contact area is circled in red there. But before it fully loses its grip on the seamount, go on to the next slide. This eastern ice shelf is likely to shatter into hundreds of icebergs, just like the shattering of your car's window. Over the last few years, just since 2016, we've seen fractures propagating at alarming rates, well over 10 kilometers a year for short bursts of time. Each new satellite image we show, each new satellite image we get, we see deeper and longer fractures. The tips of some of these fractures actually are just a few kilometers away from where our team is headed right now. Those are the red and green dots in the satellite images and the red dot on the plot. An additional complicating factor is that underneath the red and green dots that are our field sites is weaker, thinner ice with quiescent or latent basal crevasses waiting to be reawakened. Next slide. This weak zone is shown here in this cutaway perspective view, which uses a satellite image as well. And in this figure, ice is flowing from the left off the continent and out towards the right onto the ice shelf and into the ocean. And here we're looking across it at that seamount in the far back corner. You can see my writing back there. I cut away a chunk of this ice and in a cartoon manner showed what the ice looks like from underneath. The rapidly propagating fractures shown in arrows there are headed right into this area of thinner, weak ice. And we believe that when these fractures propagate into this weak zone, new fractures will initiate in different directions, leading to a more rapid demise, possibly within a few years. So the next slide will just come back to my beginning point, and I'll return this, pass the story on to Peter, just reminding that there's 3 drivers of collapse: the melting by the ocean, the loosening grip on the seamount, and these rapidly propagating fractures.
Thanks, Erin. Hi everyone. I'm Peter Davis. I'm a physical oceanographer at the British Antarctic Survey. So as Ted spoke about, the Thwaites Glacier collaboration covers a whole host of ice and sea-based projects that are all designed to understand the processes controlling the fate of Thwaites Glacier. For the melt project though, excuse me, we focused entirely on understanding the processes operating in this region known as the grounding zone. And this is the region I've highlighted in red here. And this is where Thwaites Glacier first lifts off the seabed to become a floating ice shelf. Understanding the interactions between the ice and the ocean here are critical to improving our projections of future sea level rise, because the processes that operate here strongly influence how quickly that grounding zone migrates inland and how much grounded ice is therefore lost to the ocean. The grounding zone on Thwaites though lies under about 650 meters of ice. So our first challenge is to drill an access hole using hot water so we can get to the area of interest. So hot water drilling is actually a relatively simple process that relies on pumping large quantities of hot water as quickly as possible into the ice to create a narrow access hole. So the process starts in the top left with us shoveling approximately 10 tons of snow, manually shoveling about 10 tons of snow into these portable tanks to generate around 10,000 liters of water. This water is then heated to about 80-90 degrees using this bank of heaters on the top right, before pumped through the drill hose, over the drill tower and down into the ice through the nozzle, which you can see in the bottom left. From start to finish, it takes about 24 hours to drill an access hole on Thwaites Glacier. The speed is controlled by the temperature of the water and the diameter that we need the hole to be. So patience is key. Next slide, please. So using this access hole, we were able to take the very first observations within 2 kilometers of the Thwaites grounding line itself. We found a very narrow 54-meter deep water column. So this is quite narrow because, of course, we're quite close to where the ice shelf first lifts off the bed. And we found that the water column was characterized by strong gradients in temperature and salinity. So in this panel labeled 1. The temperature of the ice base is 1.5 degrees above the freezing point, indicating that there's plenty of deep ocean heat. As Erin pointed out, there's plenty of deep ocean heat available in the grounding zone to drive basal melting. So through the borehole, we also deployed a remotely operated vehicle that my colleague Peter Washam will talk more about next. And we used that to survey how quickly the ocean was moving, the ocean currents essentially, within the grounding zone region, all the way up to the grounding line itself. And what we found is that the currents were very weak. They average only about 2.6 centimeters per second. And the key message here is that weak currents tend to lead to lower basal melting. So we have a picture where we have high temperatures to drive basal melting and low currents that tend to lower basal melting, so they counteract each other. Next slide, please. So we're also able to leave sensors behind in the grounding zone to monitor how the ocean conditions change through time. And what we found is that during 2020, the grounding zone becomes warmer and saltier due to ocean conditions changing outside of the cavity. So this shows there's a link between what's happening outside the cavity and what's happening at the grounding line. And overall, what it demonstrates is that more deep ocean heat was available to drive basal melting as it arrived at the grounding line. So throughout 2020, the thermal driving, so this is the difference between the in situ temperature and the in situ freezing point, increased to over 2 degrees centigrade. However, using radars we deploy at the surface to measure the melt rate directly, the melt rate's actually pretty small on Thwaites Glacier grounding zone. It's only about between 3 and 5 meters per year. And this is about an order of magnitude less than we see on other grounding zones. So what we're basically seeing is despite the high ocean temperatures, the basal melt rate is quite depressed because of the weak ocean currents. And overall, the take-home message is that this suggests that the rapid grounding line retreat we've seen beneath Thwaites has been associated with relatively modest basal melting, despite the high ocean temperatures. So I'd like to hand over now to my colleague, Peter Washam, who will talk more about the ice fin.
Hello, my name is Peter Washam. I'm a research associate at Cornell University. And as my colleague Peter Davis pointed out, I will be talking about more of the observations from ice fin in this grounding zone region. So ice fin shown in the bottom part of this panel, sorry, slide, as this long and skinny yellow robot, which again, we deploy through the borehole. And it's a great tool to get spatial pictures of the ice, ocean, and seafloor in this region, which is helpful because it allows us to really get a good understanding of the holistic picture in this hard to reach region. Next slide. So here I'm showing data from ice fin along 2 transects in this grounding zone. T1, which you can see in this inset map, is the burgundy line, and T2, which is the navy line. So key takeaways from this is we were able to map the ice, ocean, and seafloor here over about 5 kilometers. And at T2, we were able to map these properties all the way up to the grounding line point, which you can see in the top right corner of this figure. These data depict a chaotic grounding zone, next, where the water is warm, as previously mentioned, most of which is 1.5 to 2.25 degrees above freezing, except near this grounding line within the several hundred meters of that point, which you can see in the top right of T2, where the water is colder at about 1 degree above freezing. Next, we're also able to see that the ice is rugged, where it has these corrugated features near the grounding line that, as we move away from, we observe these very large crevasses. And then finally, on the outer part of these transects, we see these step-like features, which can be seen very nicely in T1, where the ice is flat, and then there's a hard step up to a next level. We call these terraces. Next. And finally, we see that the grounding line has retreated up the seafloor slope over the past decade. So in 2011, the grounding line was mapped with remote sensing, which you see as this white star here on these figures. And then it was mapped again in 2016, where you can see these blue stars. And then finally, it is to the point where we see it now at T2, well up above those 2 stars. Next. So one of the reasons ice fin is a very nice tool is we're able to combine these different data sets to say something more meaningful. So these plots here show the melt rate along these 2 transects along the ice base. And the key takeaway here is that in the middle 2 panels, you can see these melt rates plotted along the ice base. Next, please. So the key takeaway here is that the flat ice, which you can see shown in blue here, melts relatively slowly upwards at about 2 meters a year, which is consistent with what Peter Davis showed before from the independently measured radar data. However, these crevasses are hotspots of melting where the ice melts laterally or horizontally at about 20 meters a year. Next. And this is because the slope of the ice determines the efficiency with which ocean heat and salt mix into it and drive melting. Next. And finally, we see near the grounding line, the melting is lower because of these colder, fresher ocean conditions and weaker current speeds. So this region for now is somewhat more protected from direct ocean melting. Thank you. I can pass it along now.
Okay. Hi, everyone. My name is Lizzie Klein, and I'm currently an adjunct professor at Lewis and Clark University. The work I'll be discussing today was part of my PhD research at Penn State. So the site that I am going to present from is the same as the previous two presenters, Peter Davis and Peter Washam. And what we're looking at on the right is a map view, and the black thin lines indicate the location of the grounding zone. So where it goes from sitting on a bed to floating over the ocean. And anything to the right of that grounding zone in this map is grounded, anything to the left is floating. So I want to zoom in on this red box here. So now looking at the figure on the left, what I did was collect reflection, seismic, and radar data. And what these data do is help you look at what material is beneath the ice. And so what we see in these signatures in the grounding zone and a couple kilometers upstream, so further away from the ocean, there's a lot more variability in that basal material than initially expected. There's regions where it looks like it could be rock, and then regions where it looks like it could be wet till, like mud, essentially very wet mud, and even some regions where it could be thin water. Next, please. So what this looks like is happening is a mechanism called tidal pumping. And if you imagine you have a 2D cross section of ice, ocean, and sediment interacting, what happens is when you have low tide, the floating ice shelf portion sinks down, and this acts with the lowering water. And this acts kind of like a lever and can actually pull up a section a little bit inland that can pull water in. And then the opposite happens when you have high tide and the water level rises, the floating section rises up, and then a little bit inland, you have a leveraging down kind of phenomenon. And so this up and down motion in the grounding zone and a couple kilometers upstream can kind of pull water in. So the main takeaways from the evidence for this tidal pumping is that we have data evidence supporting that this process is happening, which has not been too frequently observed elsewhere. And also, given the warm water that's beneath Thwaites, this tidal pumping could have really big implications for the melting and stability of the grounding zone of Thwaites. Next, please. Okay, now what we're looking at is a 2D profile of the radar data set. So on the right side of the figure is that area where the ice is sitting on the bedrock, and on the left side of the figures where you have the glacial ice floating over the ocean. And this orange line I'm pointing out here is the ice fin data that the previous two presenters showed, where you have the seafloor and the bottom of the ice shelf with the crevasses in it captured. So now we're looking about 5 kilometers further downstream on the floating ice shelf. And I want to talk about this basal feature here. This is very large compared to the crevasses we were just talking about. Next slide, please. So the interesting thing about this feature is that it's in ice that we think was grounded upstream about a decade ago. So how did such a large feature form so quickly? So if you imagine you have a chunk of ice floating over the ocean, and that ice has layers in it, if you somehow rapidly melt and remove a section of the bottom of the ice shelf, then what has to happen is the ice over top that thinner section has to float a little bit lower. Imagine ice cubes in your glass of water, or a large iceberg, right? Bigger stuff floats higher. So it has to sink down, and you'll see this reflected in the internal layers. And that could potentially force open some crevasses in the top there. And then much like Peter Washam showed upstream, you can get warm water in there. The melt rates on those sloped surfaces and those crevasses is more rapid, and you can propagate the formation of this feature upwards. So this is what I think is happening here. And the takeaway is that the existence and possible rapid formation of such features could have implications for the long-term stability of the ice shelf. So how long the ice shelf will be around to provide that buttressing impact for the ice upstream. All right, that's it for me. Thank you.
Hi, everyone. My name is Anna Crawford. I'm a postdoctoral researcher at the University of St. Andrews. So in addition to the ways we've already heard about Thwaites melting and fracturing, glaciers like Thwaites could also dramatically retreat through processes called ice cliff failure and marine ice cliff instability. Next. In this figure, a vertical ice cliff may be exposed if we lose the ice shelf, so the part that's floating over the ocean. There is also a region of the Thwaites terminus that currently ends at a cliff. This is shown in the box in the inset. This area is not retreating through ice cliff failure yet, but we want to know, will ice cliff failure become a factor in the future retreat of Thwaites? Next. Using a unique 3D modeling workflow, I have quantified calving retreat rates that can be expected from ice cliff failure. Retreat through ice cliff failure is modest when ice cliffs are around the height threshold for failure to occur, but the rates of retreat dramatically accelerate as ice cliff height increases. From these retreat rates, I have derived a simple equation to represent ice cliff failure in larger scale models that look to simulate the future of the entire Antarctic ice sheet. Next. My 3D glacier modeling work also shows that ice cliff failure will occur through a range of what I call modes. Some of these examples being shown here with the termini of these idealized glaciers failing through tensile and shear failure. Next. My work and that of my colleague, Jeremy Bassis, also highlights that melange, which is an icy conglomerate that is shown here as a thinner plane in front of the glacier terminus, that this melange can inhibit ice cliff failure if it can exert enough back pressure on the ice front itself. Next. My work was conducted with a model workflow that paired two 3D models. First, glacier flow was simulated in Elmer ice. And after varying durations of flow, I would test for ice cliff failure in a model called HIDEM. This unique workflow allowed me to quantify how long of a period the glacier needed to flow over before that failure occurred. And this was not possible before and led to our retreat rate calculations that I showed earlier. Next. So we are interested in ice cliff failure, especially because it can be a component of marine ice cliff instability. And this figure is showing that after we lose any extending ice shelves and get to a situation like in T3, we'll have a vertical calving face and ice cliff above the waterline. And if that outward pressing stress that is represented by the horizontal arrows is great enough, then that stress could overpower the strength of ice, and that would lead to an ice cliff failure event. Now, if a taller ice cliff is exposed after each ice cliff failure, then that outward pressing stress is going to grow and grow, accelerating collapse and potentially initiating the self-sustaining process that we call marine ice cliff instability. And this scenario would be more likely to play out over regions that have a reverse sloping bed and large thickness gradients as we move inland, like the situation shown here. And dauntingly, much of Thwaites Glacier and the West Antarctic ice sheet sit over such reverse sloping beds. Next. Using a 2D model called M-ICE, Jeremy Bassis shows that catastrophic collapse through marine ice cliff instability can occur if ice cliff failure begins over a severe enough bed slope or ice thickness gradient. However, there are other combinations of these factors, as well as ice velocity, that would result in re-advance or slower retreat. And additional simulations with my model workflow also show that a single ice cliff failure event is not going to automatically lead to runaway retreat. Next. Now to summarize, we found that retreat rates are modest for cliffs that are just at the height threshold for ice cliff failure to initiate. There is a great acceleration to alarmingly fast retreat rates for really great ice thicknesses. However, ice flow and thinning can counter the growth of these ice cliffs, and melange can also put the brakes on ice cliff failure. We present a solution to represent ice cliff failure in these large-scale ice sheet models, and we state that melange also needs to be represented alongside it. And we are now working with colleagues who work with ice sheet models to investigate if and when ice cliff failure and marine ice cliff instability play into the retreat of Thwaites Glacier and the West Antarctic ice sheet. Thanks, all from me.
If you go ahead and click one more time, you'll see that the 8 projects that were funded by the US National Science Foundation and the United Kingdom's Natural Environmental Research Council address different parts of this whole system and work together in the future to get a further insight into how Thwaites is behaving, and in particular, what's going to happen over the rest of this century. Different projects taking a look at different aspects of the problem. And you can see some that you haven't heard from today that you will hear from in the future as we conduct the last several field seasons here in Antarctica. I want to thank the National Science Foundation and the NERC group for funding us, and AGU for hosting this press conference. I think there's one more slide. We'll take any questions now. Our goal is to assemble the data and knowledge and then advise policymakers. Thanks very much.
Okay, thank you to all of our panelists. I'm Liza Lester from AGU Media Relations, and I'll be moderating the Q&A section of this panel. So first up, we have Seth Bornstein from the Associated Press. Seth, we're going to go ahead and invite you to unmute your mic and go ahead when you're ready.
And it still tells me the host muted me.
We can hear you.
Okay, good. Thank you for doing. I have a couple for Ted and one for Erin. Ted, first, since you're out there, does what you've seen this season, are you seeing anything different, new, worse, better than previous seasons? And then more for the big picture, can tell us sort of some figures in how much change we've seen in the past 10 years to Thwaites in terms of loss, and how much is, given that, what we expect in the next 10 years. And for Erin, in one of your slides on losing the grip, you had the red and the green contact points. And I'm wondering how, there was no sense of scale there, how big a difference, and how was that between those points, and is that big or not, does it matter?
So Seth, in terms of this year, we've seen Thwaites continue to evolve. And in fact, just in the last few years, the pace of acceleration on that ice shelf area that Erin talked about has increased. And so, as well as the cracking, we've seen the fracture grow. In fact, just yesterday, we got some high resolution satellite pictures of our field site to take a closer look at just how close some of the fractures have come to where we're planning to camp. And they're still comfortably far away, but things are evolving rapidly there. In terms of what's happened at Thwaites over the last decade or so that continue to underscore how important the glacier is, it's continued to increase how much flux of ice it's putting into the ocean. It's around 50 billion tons per year, still a relatively small fraction of sea level rise, but as this whole presentation is underscored, it's upwardly mobile in terms of how much ice it could put into the ocean in the future if some of these processes continue, particularly to the point where the ice-ocean interface is much thicker ice, and therefore some of these other fracture processes begin to take hold. I think your next question was for Erin.
Yes.
Yeah, thanks, Seth. Your question was on the seamount pinning point in the red and the green lines.
Yes.
Yeah, and so that is the scale on that. It's approximately 15 kilometers from end to end there, but it is a very significant decrease in contact area. And And we are predicting if it continues on its current trend, using the current kind of processes ongoing, we expect that it will reduce down to near zero contact within a decade. And so that's our estimate so far. But other things are changing and evolving, so I don't expect it to be a nice linear trend. So it could increase more rapidly, or it could slow down and stick around, and we might have another mode of failure, which would be through that fracturing that I talked about. Does that answer your question?
So you're saying within a decade, basically, you're not, it will have no grip on the seamount, right?
At the current rate, yeah, that it's decreasing, it'll be within a decade that will lose. But we actually think that the fracturing mode is probably going to supersede that, and that will happen within a few years to 5 years. But that also is hard to put a number on, because there's so many processes going on that projecting out in a linear fashion like that is very difficult to do.
So in the fracturing, so how much gets, that's where it gets a little confusing to me. The seamount, I could almost picture a massive collapse type of thing, right?
Mm-hmm.
Fracturing, you don't see, it's less massive, right? Is that fair to say?
It will, I visualize it somewhat similar to that car window where you have a few cracks that are slowly propagating, and then suddenly you go over a bump in your car and the whole thing just starts to shatter in every direction. So a subtle change in the stress can cause the fractures to propagate more quickly. And there are a lot of weak zones. I identified one weak zone, but there's a few others that are potential weak zones that can transfer stresses and propagate fractures in multiple directions. And at that point, it might actually just bypass the seamount and go out towards the upper right on that figure. It can essentially fracture to where it just doesn't even care that seamount is there anymore. And most of the ice will go off to the upper right in that picture. If it, as it starts to lose, as the fractures start to propagate and it loses its coherent, the material just loses its ability to hold that strength and it starts flowing outwards.
Thank you.
Thanks, Seth. The next question is going to be from Jonathan Amos at the BBC. Jonathan, go ahead when you're ready.
Hi there, I hope you can hear me okay. I just wanted to pick up on what Seth is saying there. I mean, for better or worse, we've labeled this thing the Doomsday Glacier. And you guys are talking about something happening that's really dramatic. Not 50 years from now, 100 years from now, but almost in the next political cycle, the next 5 to 10 years. I assumed that this was, some way off, but you're telling us here today that we're about to see really quite dramatic change in one of the biggest glaciers in the Antarctic. Can you comment on that?
I'll say a few words. Yes, you're right. There's going to be a dramatic change in the front of the glacier, probably within less than a decade. A lot of studies, both published and what Erin has shown today, point in that direction. When that happens, the fast flow part of Thwaites is likely to widen because the bracing on the east side will be gone. It may still take a few decades before some of the other processes that accelerate the ice flow and the retreat take hold. It will, though, accelerate the pace and effectively widen the dangerous part of the glacier. And maybe some of the others want to talk about how they take Jonathan's question.
I can jump in a little bit. So the end member, the way I see it is that as Ted said, it's going to accelerate to match that faster part of the glacier, which means that this 1/3 that is flowing more slowly now could potentially triple in speed over the next, who knows how long, decades to century. And that's the part that we don't have a good handle on, is how fast the acceleration will happen. But if it accelerates to match the other 2/3 of the glacier, that's a tripling of speed of this section of the glacier. What will control that acceleration is some of what the other ITGC groups are studying. So some of the upstream, how it's moving along the rocky and sediment bottom of the ice, and how the sides of the glacier, how slippery those sides of the glacier are, where it is attached to the other ice. And there's bedrock. There's a lot happening upstream, essentially, that will moderate how quickly that acceleration can happen. So the end member is that it could triple in speed, but the rate at which it will get there depends a lot on what's happening upstream, and that's what our partners in the TIME and GHOST teams are studying.
That eastern ice shelf, what sort of area are we talking about from the grounding line to the pinning point? What area is relatively stable there on that?
It's about 1,000 square kilometers. So it's 40 or 50 kilometers long and 30-ish, 20 to 30-ish kilometers across.
Right, but if it starts to break up, if you've got these downward crevasses, you know, Peter and both Peters were talking about these upward crevasses as well, and it all sort of breaks up windscreen like. The ice tongue is going to be unconstrained as well, isn't it? I mean, that sort of mass of icebergs is going to be loosened too.
The ice tongue is already pretty loose, and it's flowing at 2 kilometers per year right now across about 80 kilometers width. And then this section we're looking at is another 40 kilometers, where right now it's only flowing at about 600 meters per year. And it could, that's why I said the tripling in speed over that, just that 40 kilometers could triple in speed when this all releases. I don't anticipate the ice tongue accelerating more at this point. Does anyone else see that?
I mean, it has accelerated gradually over the last few decades, but the big change, like you're saying, would be the loss of the ice shelf. And that's going to look like a bunch of icebergs drifting off to sea, but then behind it, we'll see the glacier pick up speed and the grounding line retreat further.
Yeah, just a really quick question for Anna. How high does a cliff have to be unsustainable? Sort of Game of Thrones ice wall kind of height? I don't know.
Well, the threshold for ice cliff failure to start occurring, we find to be around 130 to 140 meters, tall. The extreme scenarios that I was showing in that plot are something like 400 meters, of ice cliff height. That's a long ways off if we're ever going to get there, Right. So really what I was showing that, being the kind of key factor if we hit that unstable retreat or not is that thickness gradient. So how fast the ice is getting thicker inland is really going to determine if ice cliff failure takes off into that self-sustaining marine ice cliff instability or not.
And is that a freeboard height or a freeboard plus draft height?
That's just a freeboard. Yeah.
Freeboard.
Yeah.
Right.
So the ice has to be thousands of kilometers thick to still touch the seabed and support a cliff like that.
Yeah, so those are extremely extreme scenarios, but it just does show how this takes off, if we were to retreat really, really rapidly, and how it would become an accelerating process, if we hit those threshold thickness gradients. And maybe just to jump in a little bit on, the thread that Erin and Ted were just talking about, I find actually the other third of the glacier to be really interesting for this process. It's right now that part of the glacier that doesn't have an extending ice shelf or an ice tongue, is at a vertical cliff at the moment. And it's not tall enough to be, in ice cliff failure territory at the moment, but it's also sitting on a bit of a high in terms of the glacier bed or the seafloor there. So if we push that back a little bit through melting and kind of normal calving, we could dip into that basin. And that's where there's a potential for this ice cliff failure to initiate. So all to say that, every third of this glacier is interesting and potentially susceptible to major changes.
Yeah, no, you're right. And in fact, the thing that got everyone's attention was the fast flowing 2/3 of the glacier and the fact that the ice descends basically, or the bedrock descends into a really deep basin. And so those numbers for ice cliffs, super high ice cliffs, we haven't seen those yet on Earth. We've seen things that come close, but Thwaites has the kind of geometry that could really make at least the middle range of those extreme heights possible. Yes, it's daunting. It's a bit unsettling, especially standing on the ice and looking onto the ice sheet and seeing that this huge area from one side of the horizon to the other is moving at you at about a mile every year. And all by itself, this one glacier could impact, it's big enough to impact sea level significantly.
All right, thank you, Jonathan. We have a question from Alexander Witze, The Nature, for Erin Pettit. Can you talk more about the timing in which you expect the ice shelf to lose contact with the seamount, and the timing in which you expect those rapidly propagating fractures to move into the inner ice and accelerate the demise of the ice shelf?
Yeah, I mean, hopefully I covered that in my last answer, but just to reiterate, our predictions right now, based on current rates of these processes happening, is that the ice will lose contact with the seamount within about a decade, and then, but the fracture propagations are happening more quickly, and it looks from the satellite imagery that we've been following that it's going to essentially bypass that pinning point and start fracturing and falling apart despite that pinning point attachment, that seamount attachment. So the fracturing could happen within 3 to 5 years at some of the current rates, but the stresses are changing on a week-to-week basis from the satellite imagery that we keep getting. Everything looks a little bit different every time we get a new image, which is really fascinating to see. And as Ted said, it's a little bit unsettling.
And a follow-up from Alex for Ted Scambos. Can you describe the fieldwork for this season in more detail, and which teams are going where to study what?
Sure. The team that Erin and I are part of, Tarzan was the acronym on a couple of the slides. We're going to go out to the ice shelf. There are 2 stations there that are monitoring both the weather and the ice in the ice shelf, and then the ocean below. That diagram implies they're touching the seabed, but in fact, the lower sensor is just above the seabed. They've had a rough time of it. They've been out there for 2 years, and a lot of the sensors aren't working right or talking right to each other. So we're going to try to repair those. We're also going to remeasure a lot of the places that we measured in the past on the ice shelf to see how it's changed in the past 2 years. So some of the members of this team were out there 2 years ago and set up the stations and did the initial survey of the ice thickness and the ice layering within the interior and some of the fracturing. Now, the other projects that are going to happen this year, there's a major cruise coming in mostly February and into March that'll be looking at the ocean right out in front of the ice shelf and the front of Thwaites Glacier, the center part of Thwaites Glacier. And there's quite a bit of science associated with that cruise on the ship called the Nathaniel B. Palmer. I think it's 45 or so scientists on board that ship for 6 weeks or so. So there'll be quite a lot of field work done this season. Another group that's further upstream, and this got mentioned a little bit by Erin, that's studying how the ice in the faster flow part of the glacier is slipping past ice that isn't moving so fast. And the question there is, what's going to happen as the glacier accelerates? Will it draw that shear margin in towards the center and narrow the glacier, or will it widen the glacier through greater shear stress? There's also questions about what that rapid shear does to the ice, reorienting crystals and creating what we call a fabric of crystals inside the ice that can accelerate how fast it slips out. That's a pretty good summary of what's going on this year. There are other projects in the same area that aren't directly a part of the International Thwaites Glacier collaboration, but they still contribute to our knowledge of West Antarctica. Projects that are studying GPS and seismic data and weather stations. altogether, we're focused on West Antarctica, and in particular Thwaites Glacier, because of the threat that it poses in a relatively near time frame for geologic process. This is something that's on a human scale for sure, and therefore it's important to study now.
And can I just jump in and say that one of the exciting things on the ship-based work that Ted mentioned is that we are going to be sending some underwater, some autonomous vehicles, the little yellow ones you can see in here, but we are sending some autonomous vehicles underneath the ice shelf to swim hopefully tens of kilometers underneath the ice shelf to collect a more distributed picture of the flow under there, to go along with the mooring, the through ice instruments that are deployed through the hole in the ice. So we're pretty excited about this, the ocean work in conjunction with the ice work that Ted is leading up.
All right, our next question will be from Sarah Kaplan from the Washington Post. Sarah, go ahead when you're ready.
Thank you, guys. And I'm sorry, I'm on a train right now, and so my connection has been going a little bit in and out. But I wanted to ask, I guess maybe particularly for Erin and Ted, but really for all of you, given that this had been previously the more stable part of the Thwaites ice shelf, can you talk a little bit about the process of realizing sort of what was happening, the speed at which it could be happening, and kind of like this last stable buttress is no longer as stable as it had previously been? Like, what was there a moment either on the ice or looking at your data where you sort of realized like, oh, this is unsettling, as multiple of you have put it, and also how surprising is that? Like, is this something you were expecting to happen eventually? Is this happening faster than you'd been anticipating?
I'll just say that satellite mapping of Antarctica, and I showed a satellite map that had red patches, and Thwaites is in the center of one of the bigger red patches. Other means of using satellites really identified Thwaites and the ice shelf as a place that was changing. There really hadn't been a lot of visitors on this part of Thwaites ever. But the satellite data helped show that this was an area that needed to be focused on. So in terms of a realization, I think there's been several for all of the field work. I mean, I think there were some thrilling things that came out of the borehole science right at the grounding line, with the robot looking around, poking around, and also the long-term measurement showing ocean eating away at the ice sheet, sort of right before our eyes. So I don't know, maybe Peter would want to address that a little bit. I think Erin might also have something to say about realizations from the data.
I'll just jump in really quickly and then pass it on to Peter and Peter. But I think one of the points that I realized that this was going to happen a lot faster than I thought was when we were in McMurdo 2 years ago, and we started looking in detail at high resolution imagery of the field site we were planning to go to in the middle of this, what looked like the most boring part of the Eastern Ice Shelf, because that was also the safest part. So we had designed our field plan around going to a very nice, safe part of the ice shelf. And we got these satellite images in that showed this crack propagating, this big rift in the ice propagating straight towards our field site. And as we're sitting there standing around, we're sitting there around the big table looking at these images and watching the propagation of this crack through a sequence of images, we actually just all had to take a pause and just understand whether or not this crack was actually going to break through our field site while we were out there. And once we kind of took that deep breath and looked at it again and realized it wasn't quite going that fast, we were okay. But it still was hugely surprising to me that this was rapidly changing that fast. So I do remember that moment.
What's our nickname for that crack?
The dagger.
The dagger.
So I think to jump in and kind of talk about the ocean perspective, I suppose one of the things is that we don't know what's happening in the ocean until we drill through it. We can't observe the grounding line from space. We can't send an autonomous vehicle from the ice front there because it's too far away. So I think a lot of what was surprising for us was because we didn't actually know what to expect in the first place. It was the first time we drilled into this grounding zone. So I think the large amount of heat available, that was expected. I think we would have been incredibly surprised if we found something that didn't have that sort of characteristic. But I think what is surprising is how slow the flow speeds are, and kind of arguably in terms of the vertical melting, how little it is melting in the vertical. Of course, what is interesting, I suppose, it doesn't mean it's not changing quickly. I think we've heard a lot about how the ice shelf is responding rapidly, despite the low melting at the grounding zone. So I think that's quite a key message. And it goes to show kind of what Erin's talking about, that there are these three processes, and perhaps the ocean, the grounding zone is not perhaps the one that's driving the major changes on Thwaites, and it's the kind of the ice dynamics and the pinning points. But I will hand over to Peter, because I think some of the other surprising things are what Iceland found, and the kind of the difference between the vertical and the horizontal.
Yeah, and another thing that was really nice to see is that the seabed is sloping upwards towards the grounding line. However, we still see about 1 to 2 kilometers of grounding line retreat over the last decade. And typically we consider that configuration of seafloor slope to be more stable. So then you have to look upstream of where the current grounding line is to get a better read on how that might evolve in the future. So certainly it was a bizarre environment to send instrumentation into, and Iceland was really critical in measuring or sort of getting a good estimate on what's happening on all these different slopes of the ice space relative to the ocean forcing. And so the vertical melting, if you sort of take all that region and integrate the area times the melt rate, you see that the vertical melting, this sort of slow upwards melting is the majority of the melt. However, there's these sort of hot spots of melting where you can melt sort of horizontally. And what's sort of concerning is that when you have crevasses and other features spaced relatively close together, that horizontal melting begins to be a little more important when you can sort of mesh things together, as what Lizzie showed with that basal feature downstream. So certainly there's this localized hot spot of melting in these crevasses, and even on these smaller features where something with a steep vertical face can just melt sideways and take out chunks of the ice, but it's still a localized process. However, it's important, and it definitely plays a role in the state of the ice. So yeah, I think that's all I'll say for that.
All right, we have a few more questions, and we're going to try to get to all of them in the last couple of minutes here. Adam Vaughn from New Scientist Magazine, go ahead when you're ready.
Hi all, thanks for doing this. I just wanted to ask a couple of questions, if I may. I just wondered how much better we're getting at constraining our sea level projections from Thwaites using all the great observations you're collecting. I wondered what sort of numbers, timelines are we now putting on the sea level rise side of it because of the work you're doing. And I just want to double check. I think you said this earlier, Ted, but Anna, I just wanted to double check with you. The ice cliff collapse is still not something we've actually observed, is it? And I just wondered if we're going to if there's anything we're doing about getting better at monitoring to see if that might happen, when you're not down there during one of the seasons. I just wondered if you could speak a little bit more about that.
If you're talking about ice cliff failure, there are some glaciers in Greenland that come close to this sort of process. And in fact, that kind of kicked off some of the modeling and the interest in the whole concept of what happens with really tall ice cliffs. And in fact, one thing to say is we're watching a world that's doing things that we haven't really seen before. I mean, the ice is responding in some ways that are surprising us because we're pushing on climate extremely rapidly with CO2 emissions and greenhouse forcing. So in terms of refining our projections, that is a goal of the ITGC and a goal of a lot of groups that are working on ice sheets and what sort of things cause them to retreat faster in a warming climate. I think we are going to make some progress in terms of forecasting how Thwaites will unfold, in large part due to Anna's work, and she mentioned her colleague, Jeremy Bassis. That's an important component. And the thing that I want to draw attention, spotlight on her work, is the fact that getting a time, a rate basically for how fast fracturing happens is kind of a breakthrough, because a fracture process is very difficult to model. And getting a time for something, when something will crack, that's a fundamentally difficult problem in physics. Maybe Anna wants to pick it up from there.
I know we're running out of time, so I'll see what I can say. So by joining these two models, I was able to quantify what I call that time to failure. So what Ted was describing as how the fracture that happens after the glacier flows for a certain amount of time. And that was a major jump, in the modeling of ice cliff failure, because before many assumptions need to be made about when that failure occurred. So that allowed us to calculate those retreat rates that I was showing and derive that equation that can now represent ice cliff failure in a more informed manner in these large scale ice sheet models. And I'll just kind of highlight a poster, if you're going to any of these other events at AGU, a poster by Matthew Morlahem, who is an ITGC member who is working with that equation that I derived to see how it is implicated in the retreat of the Pine Island and Thwaites glaciers. So I would point you over there to learn more about it.
Thanks very much, both.
All right, we're going to fit in just one more question and then we're right up against the hour. So I apologize to the two additional reporters who have questions here in the queue. If you want to email those to us, we'll make sure that the panelists are able to get back to you with an answer to your question. The final question from Harvey Leifert, freelancer for TED. Have you made any suggestions to policymakers yet based on what you've told us today?
Well, yeah, we have actually not so much suggestions or recommendations to policymakers. Those are, I think, fairly obvious and fairly broad. That's a thorny issue, but we have reported to the British Parliament for one, and other groups that are interested in informing Congress for another about the results of ITGC and the progress of the research there. And that's an ongoing thing. I kind of stumbled over one of my last slides, which was intended to show that our data gathering and then our synthesis is intended to inform policymakers through predictive papers that talk about both the future behavior and lessons learned from past behavior of Thwaites Glacier. That's also a part of ITGC. That will help characterize what the next century is going to be like from this part of Antarctica. We think it's going to be led by changes in Thwaites Glacier.
Okay, and with that, I want to thank our panelists for sharing your work, and for other reporters and journalists who attended this session. This concludes our first press conference. Our next event, a press briefing on updates from the latest IPCC report, will begin at 11 a.m. Central Time. And thank you for joining us.
Shall we have a little chat with each other?
Sure.
Wait for the others to leave.
Yeah.